Welcome to our CSEC Chemistry Examination Preparation Sessions, being facilitated by the Individualized Science Learning Center. In this session, we're looking at organic chemistry. This is the question that we're looking at. We're told that organic molecules can exist as different structural isomers, and we're asked to define the term structural isomers. So in organic chemistry, molecules normally have a molecular formula, which tells us exactly how many atoms of each element are present in that molecule. Now, when organic molecules have the same molecular formula, but how the atoms are arranged are different, we say that they are forming structural isomers. So structural isomers have the same molecular formula, but a different structural formula, or they differ in how the atoms are bonded or arranged. Let's look at the second part of the question. We're given a particular molecule with the formula C4H10, and we're told that it can exist as structural isomers. And so we may remember that structural isomers have the same molecular formula, so they'll have the same C4H10 formula, but how they are arranged would be different. And in this question, we're asked to particularly draw the fully displayed structure, right? So it must be fully displayed, showing all the bonds and how they are connected. So what type of compound is C4H10? What type of molecule is that? Because it's C4, we note that in terms of naming, we would have a prefix but, B-U-T, and of course it has 10 hydrogens, so we can determine the type of homologous series we're dealing with, which would be an alkane. So we're looking at butane. And generally, when we're drawing structural isomers, you can draw the straight chain isomer first. So for butane, having 4 carbons joined in a straight link, and the requisite number of hydrogens added so that carbon has 4 bonds would represent isomer 1, butane. Now, how could we get a second isomer? Usually, to get a second isomer, a quick way to do that is to form a branch. And we form a branch when we have a carbon that is attached to another carbon in between 2 other carbons. Sounds confusing, right? So in this case, if we add a methyl group, so we move one of the CH3 groups at the end and place it in the middle, we now have an isomer. And to name this isomer, we note that our branch is a methyl group, CH3 group, so it's an alkyl group. And it's on the second carbon if we count from either direction. And so it is 2-methyl propane. The question continues, showing us that we have 2 hydrocarbons, A and B, and we're asked to describe a test to distinguish between compounds A and B. So whenever we're asked to distinguish or work out what these compounds are, we need to note the actual type of compound that we're dealing with. So we need to note the type of organic compound or the homologous series. And of course, by examining compounds A and B, we know that A has a double bond, so that would represent an alkene, and B, having only single bonds, would represent an alkane. So how do we distinguish between an alkane and an alkene? Very common test is to react them with bromine solution, that's one, or we could also add acidified potassium permanganate solution to a sample of compounds A and B. So those are 2 distinguishing tests. And what would we observe? In a test like that, The alkenes, so all alkenes would react with a bromine solution. So compound A would decolorize the bromine solution. It would also decolorize the acidified potassium permanganate solution, whereas compound B, being an alkane, would not have a reaction. Let's continue. Still using compounds A and B. We're told that both compounds A and B would burn in oxygen, and we're told to give a balanced chemical equation for the burning of compound B in excess oxygen. So let us note that the question says excess oxygen. So in organic chemistry, substances can burn in excess oxygen or in limited oxygen. In excess oxygen, we can produce carbon dioxide and water or steam, whereas in limited oxygen, we could produce carbon monoxide or carbon, if it's very limited, which is the black looking soot, and water or steam. So in this particular equation, let us write down our reactants and the products we expect to get. So it is compound B, which is C3H8, that's a formula, burning in oxygen to give us carbon dioxide and water. And of course, we put in our state symbols. Now, because we want a balanced chemical equation, we have to now look at the number of atoms on both sides of the equation. So we have 3 carbons on our left and 1 on our right. How can we make that balanced? We have 8 hydrogens on our left and 2 on our right. How can we make that balanced? And generally, when we're balancing equations, we would leave the oxygen for last. So to balance that, you may realize we would need 3 carbons on the right, yes, 4 H2 to balance the 8 on the left. And as I said, when we count up the number of oxygens remaining, so we have 3, 2, 6, and 4, 10, means that we would need 5 O2 to balance the oxygen. Good job. Now the question continues, showing us the same 2 compounds, compounds A and B, and we're asked to give a use for each of those compounds. So it's good to recognize that compounds A and B would normally be found in the refinery gas fraction when we're distilling or bringing crude oil through fractional distillation. So it means generally any substance found in the refinery gas section can be useful as a fuel. To be specific though, compound A, which is propene, can be used in the manufacture of a polymer called polypropene. You can see that on some of these plastics that's used for packaging and for containers. Propene is also useful in the production of propanol, very important chemical. Compound B is propane, and of course, we're used to using propane as fuel for our stoves, for cooking, and for heating. Now, the question continues now to using compound A, we're told that it reacts with a substance X in the presence of concentrated sulfuric acid at 170 degrees Celsius to form compound D. Again, it's useful to look carefully at the structures to identify the type of compounds we're dealing with, or in this case, the functional groups. So we have compound A, which would represent our alkene, and compound D has an OH group, which would represent our alcohols. So that's the first thing. How can we convert an alkene to an alcohol? This normally occurs, of course, using the hydration reaction, where alkenes react with some substance to form an alcohol. Now, if it's hydration, we could, use our simple reasoning to say When substances are hydrated, we add water. So in this case, X would be water in the form of steam. So when we add steam to an alkene, it can be converted into an alcohol if it is done in the presence of concentrated acid. So we're asked now, what is the name of compound D and the homologous series to which it belongs? So we may have gotten a part of that answer already. Naming, we note we have 3 carbons in compound D, but there's an OH group, and the OH group is now placed on the second carbon. So we have to account for that in the name. So compound D would represent propan 2-ol 2 to show that the OH group is on the second carbon. And of course, we know that that is an alcohol, or it may be called alkanol. Good job, students. Remember, if you need further help in your CSEC examination preparation, like and subscribe to this channel, and also you can email us at the email address indicated to get further one-on-one help. All the best in your examination.